Hello everyone. I'm going to be talking about our Lab 3 operational amplifier circuits. Now, operational amplifiers or op-amps are very valuable devices that are useful for many applications related to instrumentation, signal conditioning, amplification, or whatnot. Now, they are called operational amplifiers based in part for their utility in performing mathematical operations like multiplication, addition, and subtraction. But they are capable of doing many other applications. So now, in this lab, what you're going to be doing is building a non-inverting amplifier circuit. So that's this one here, non-inverting amplifier circuit. An inverting summing amplifier circuit, and also a voltage comparator circuit, okay, using op-amps. And in the end, what we're going to do is detect a simulated human heartbeat from our waveform generator. As part of this lab, we're going to explore the properties of the op-amps that we've discussed in lecture, and that's going to be that the input current into the op-amp is 0, and that when you have negative feedback, that the positive and negative input terminals have the same voltage. Okay, so that's a virtual short circuit. Okay, so so that was this part, the fundamental properties and limitations. Limitations are also going to be the voltage swing that the output of the op-amp can go to. So now, in terms of preparing for this lab, of course you should read the handout and familiarize yourself with what you're going to be doing in the lab and do the pre-lab assignment. But you may also want to refer to the video that we have that describes the basics of op-amps. That video was created to help you prepare for the final exam, but it goes over basic op-amp circuits and helps you understand what's happening with them. And then another useful video actually that you can watch is the oscilloscope video, where we go through how to use the oscilloscope, because you're going to be using the oscilloscope in this lab, and if you've forgotten how to use it, then you might need a refresher, because we will be using the oscilloscope and the waveform generator within the oscilloscope. Okay, so let's get started talking about this lab. So we talk about the background review. So up here we have the inverting amplifier, okay, and what its function is. Okay, let's go blue. So this output voltage is going to be V out is equal to minus RF over RS times V in. Okay, so this is the non-inverting amplifier, and this is the mathematical operation it does. Okay, so what it does is it scales the input voltage V in, right? So the input voltage V in gets scaled by this value here minus RF over RS. So that's the resistor value RF, which is up here, and then the resistor value RS, which is on the denominator, that's down there. So and then of course there's the negative, so that's the inverting part of the amplifier configuration. Now this part in orange that I've drawn is what's called the closed loop gain, or AV, okay, and that is described right here mathematically. Okay, AV is equal to V out divided by V in. Okay, so this here is, that part is equal to AV, okay, which is also equal to V out divided by V in. Okay, so now you should know how to get this this equation by deriving it from the op-amp summing point constraints. So the summing point constraints are the thing that we talk about in lecture, which is if you have negative feedback, the voltages at the input here and here are at the same voltage level. Okay, so that's considered a virtual short circuit, and there's no current flowing into the op-amp terminals. Okay, so that's 0 amps, 0 amps. So those are the summing point constraints. Okay, so those are the summing point constraints. Okay, so let's continue. Okay, so that's the basics of the amplifier, inverting amplifier. Okay, so then let's keep going and look at the other ones. So over here we have the non-inverting amplifier configuration. Okay, so the non-inverting amplifier, it has an equation which is V out is going to be equal to 1 plus RF divided by RS, and that's times Vin. Okay, so that's the equation, and you should be able to derive that. Okay, so that's the equation that describes the operation of this op-amp. And then down here, the next one is the inverting summing amplifier. Okay, so what it does is it takes two input signals, in fact. So we have one input signal here, some V1, and another one V2, and what it does is it adds them up to produce the output. Okay, so now let's see what the equation is. So I'll just write it down so that you have it. So it's V out is equal to minus RF divided by R1, okay, and then times V1, so that's the input voltage, and then plus RF divided by R2 times V2. Okay, so that's the equation for the inverting summing amplifier for this circuit that we see. And so, of course, this part is the inverting part, okay, the negative sign that inverts a signal. And then the summing part, of course, is this addition. So it adds the two signals, okay? But we may find it, well, I'll just put a little box around it because that's an important equation. But we may find it maybe perhaps more handy to think of that equation by just multiplying out the negative sign through it. So RF over R1 times V1 minus RF over R2 V2. That might be easier to work with in some cases. So think about that equation as well. Okay. So those are the basic circuits. Oh, and up here we have a great circuit, and that's a voltage comparator. So what this does, this is a voltage comparator, and what it does is if the positive input, so the positive input is here, if the positive input is greater in value than the voltage of the negative input, so let's say, let's draw it like this. Okay, let's label it, this is VP, and this one is VN, okay? VN for negative, and VP for positive, okay? So, if VP is greater in voltage than VN, then V out becomes equal to plus VCC, okay? Otherwise, if VP is less than VN, then V out becomes negative VEE, okay? So where's plus VEE and minus plus VCC and minus VEE? Okay, well, it's up here. So this is plus VCC, and down here is minus VEE. So in this lab, and what these are the supply voltages. So we need to power the op-amp from an external source. So this is where they get their power from, or their energy. Okay, so then in our lab, we're going to make this equal to plus 15 volts, and we're going to make this one equal to minus 15 volts, okay? So you got to make sure you don't forget to put the power in there. So now, well, why do we have the power shown for the voltage comparator here, but we don't have it shown for the other op-amps? Why is that? Well, because it's been omitted. In fact, we have to have that. So we have to add, plus 15 volts supply and a minus 15 volt supply here. And we have to do it on this one as well. Plus 15 volts and minus 15 volts. And of course, for the one that we did up here, we need to do the same, okay? Plus 15 volts, minus 15 volts, okay? If we don't have the supply voltages connected to the op-amp, it won't work, okay? So, but the thing is, what's important to keep in mind, op-amp circuits are often drawn without those power supplies drawn in there explicitly, okay? So you just have to watch out. But you always have to have the power connected. Okay. And in fact, the voltage comparator here also tells us something very important about the op-amp behavior, and that is that the op-amp, its output cannot range above its positive supply. So in this case, it can't go above 15 volts or below minus 15 volts. It has to stay within the range of plus or minus 15 volts, okay? And in fact, with the op-amp that you're going to be using in the lab, it won't even reach its full scale. It might only go up to 12 volts or 13 volts instead of all the way up to 15 volts, and it might only go down to negative 12 or 13 volts. It won't reach minus 15 volts. There are special op-amps that can do that, and they're called rail-to-rail, so they can hit the full range. But the 741 op-amp that we're using cannot go to its full range. Okay. So let's talk about the pre-lab exercises. So now the pre-lab exercises, you have to do some work, do some calculations, and predict the behavior of the circuits that you're going to be building in the lab. And then whatever you're going to be doing in the pre-lab exercises, you're going to be building in the lab period itself and testing to make sure that you get the same results, okay? So when we go through the pre-lab exercises, it's like going through the lab procedure. Okay, so let's take a look here. You have to do the non-inverting amplifier exercise. So you have to derive an expression for V out in terms of RS, RF, and V in, okay? And that's for the op-amp circuit here. Right here. Okay? That one. Okay. So what's that going to look like? Well, the expression that you're going to get, right, it's for the non-inverting amplifier, right? So it's going to be V out is going to be equal to 1 plus RF over RS times V in. So what you're going to have to do is derive that from the basic op-amp summing point constraints, okay? So you know that there's a virtual short between VP and VN, and no current flows into the op-amp terminals, okay? So you have to derive this equation, and you can use node voltage analysis to do that. Okay. So then, once you do that, you're going to calculate V out when you have certain values. So RS is going to be 2.2 kilo ohms, RF is going to be 1 kilo ohm, and V in is going to be 5 volts. Okay, so then in the circuit here, so let's just say RF, what did we say it's going to be? 1 kilo ohm. RS is going to be 2.2, so that's 2.2 kilo ohm. Okay, and then this Vn is going to be 5 volts. Okay, so now we said you're going to be building these circuits in the procedure, so let's think about this for a second and think, okay, where are you going to get the 5 volts from, right? You're going to get it from your breadboard system, right? Your breadboard system is going to give you plus 15 volts, minus 15 volts, and it also has plus 5 volts as well. And you got to be careful how you connect the plus 5 volts, okay? Because you need to reference that plus 5 volts to the plus or minus 15 volts on your breadboard, okay? So you have to make a connection from the ground between the plus 15 volts and the minus 15 volts, and you've got to put a wire into the right place for the 5 volt supply. If you don't know what I'm talking about, you might want to refer to the breadboard video that we made, okay? Because it explains that there. Or you can ask your TA or instructor. Okay, so and then, okay, so then you do that and you calculate what the output voltage is supposed to be. So that's the output voltage that you're supposed to calculate based on your equation and those values. And you're supposed to determine the closed loop gain, which, as well you recall, was AV, the closed loop gain, is equal to V out over V in. So it's basically this part, right? that's equal to AV, right? Okay, so then you repeat the previous step, repeat the step with a 1 kilo ohm resistor connected from the output of the op amp, to the reference node. What does that mean? What does that mean? So what that means is this. You put a resistor, I'm going to go back up to the drawing, you put a resistor here. Okay, and its value is 1 kilo ohm. So that's a 1 kilo ohm resistor. Okay, so now you're supposed to predict what's supposed to happen. Okay, so you can do that with your calculations, and then see how it goes. So now that is a good exam question too. Okay, that kind of stuff appears on exams, so you should understand what's happening there. Okay, and then the last step here in that procedure is to repeat step 2 with RF equal to 8.2 kilo ohms. So what does that mean? So RF is 8.2, and it was 1 kilo ohm. So then let's just say that 1 kilo ohm becomes 8.2 kilo ohms. Okay? And you repeat your analysis. Okay. So let's see what the next one is. It's the inverting summing amplifier. Okay. So let's write out what that equation was. Okay. So that equation was V out is equal to minus RF over R1 times V1 minus RF over R2 times V2. Okay? So remember that circuit was this one here. So that's this circuit right here. Okay? So that's the circuit we're going to be playing with. Okay. So then, okay, now we got both on the screen. Very nice. Okay, so now you're supposed to do some design, and what you're given as design parameters is you want the voltage gain AV1 to be minus 10.85, okay? And then the next thing is the AV2 has got to be minus 0.667, okay? So what are these AVs, okay? So right here I'm going to show you. So this right here, this part is equal to AV1. You can imagine that's V out divided by V1. Okay? V out divided by V1. Right? Just like it says in the formula, V out divided by V1. Okay? And we could say that's V out. Okay? Maybe that makes it a little bit more clear. And then the second one, this guy here, okay, that's equal to AV2, and that's equal to V out over V2. Okay? So you have to calculate this, and it gives you a constraint here. The values of R1, R2, and RF must be not less than 4.7 kiloohms. Okay? So that's a restriction. They have to be 4.7 kiloohms or above, okay? None of them can be below. And to make the right values, you may not have exactly the right values, but these are the resistors that we have available in the lab, and you may need to make some series, parallel, or whatever combinations to come up with the right resistor values. Okay. So then we're going to build the circuit. So this is up here on the left. There's a very handy translation of the symbol, right? This is the symbol, what we're working on, to the physical chip. Okay, so this is what the physical chip looks like, and the pin numbering goes like this, right? It goes 1. So first of all, where do you start? You see this notch here? Okay, that orients which way you're going to start counting the pins. And to the immediate left of that notch, you have pin 1, and then you count down going counterclockwise, so pin 2, pin 3, pin 4, then you come across to the right, and you got pin 5, then go up to get pin 6, 7, and 8. So that's how the numbering works. So, and then we have the names of the pins as well. Okay. Now in this lab, it's a 741 op-amp lab, and since in the first lab you actually made the same circuit except with discrete components, your board will work exactly the same as this chip. Although its performance won't be quite as good as the chip, it'll still work quite well and perfectly fine for the purposes of this lab. So you can use your op-amp board. And what's so nice about it, there's that notch part that I told you about, and then you know, over here is going to be pin 1, pin 2, pin 3, pin 4, 5, 6, 7, 8, and it's really nicely labeled on your board with the name as well as the pin number. So it's been really nicely done. And in fact, you have 3 little pins for every pin on the op-amp. So it's a super nice board. So now, how do you plug that chip in to the breadboard? Okay, so this is what this picture is showing. So this is the 741 op-amp chip being plugged into the board. Now, remember how the nodes worked on the breadboard. So, right, all these 5 are connected to each other, right? Okay, and then the 5 on the other side, let's say over here, they're connected to each other, but they're not connected across, okay? So these 2 are not connected to each other, okay? There's no connection, okay? Because we have a break. This is a break in between the 2 sides, okay? So that is where we put the chips. Okay, so that's where we put the op amp, and it straddles across that break. Okay, so then its pins have are connected. You know, like here's one node here. So if you want to connect to that pin, you plug in there. You plug in here for the next node. Plug in there for the next node. Plug in there for the next node, etc., etc. Okay. So you can see some wires have already been plugged in. So that's how you use the op amp chip in the breadboard. Okay. It might be a little bit more tricky to use the big printed circuit board that you have over here, but that's just how it is. Okay. So then you're going to go ahead and build the circuits that we just talked about for the Prelab exercises. So you're going to build each one of those, and just be careful when you're building, and do a good job. So now over here, this is the part where you will measure the summing point constraints. Okay, and then so now over here we're going to measure and record the current entering the op amp at the non-inverting terminal, and at the like, do we do it at the other terminal too, or just the one? I guess just the one terminal. Okay, let's see. Okay, sure, that's fine. So this is a non-inverting op amp, right? So let's just well, I could just go back up to the drawing. Okay, so I don't have to redraw it. Okay, over here we're going to be checking what's going into the non-inverting terminal. Okay, sorry, one quick sec. Yeah, non-inverting terminal. So that is this one right here. So let me get rid of some of this color. Okay, so what we're going to do is we're going to make a break in the circuit right here. Okay, that's a non-inverting terminal. We're going to make a break in there. Okay, so oh, here, let's do it with white. Okay, we're going to break the circuit here. Okay, and then we're going to insert our ammeter. So I'm just going to say my ammeter is here. That's ammeter, and it's going to measure current, right? And then I'm going to put, let's say, the red lead of the ammeter over here, and then the black lead of the ammeter over here. And then what we're going to do is measure how much current is flowing into the op amp terminal. Because remember, our summing point constraint said that there's no current that's supposed to flow in there, so we're going to measure to see how much current is actually flowing. Okay, so that's that measurement. So that's the one that we just talked about here. So that's this one right here. Okay, that's A. So then we're supposed to replace that connection between the voltage source and the pin 3. And then we're going to measure the voltage between the op amp input terminals. Okay, so we're doing this one now, right? Okay, so let's go back up to that drawing and see what that measurement looks like. Okay, so now I'm going to get rid of what I did. So I'm restoring the circuit back to how it was. So now it's like a working op amp circuit. And I guess at this point we're not going to have that resistor there. Anyway, so then I'm going to have my voltmeter, VM, and then I'm going to connect the voltmeter to measure the voltage between the two input terminals. So let's say my red lead would go to this input, and my black lead would go to this input. Okay, and then I'll measure the voltage. And so remember the summing point constraints for the op amp. If we have negative feedback, then there's a virtual short circuit between the two input nodes. So my voltmeter should ideally measure 0 volts. Okay, it should appear like a short circuit, even though there's no wire that looks like it's connecting these two together, right? So these two, it looks like they're connected. Okay, that's what virtual short circuit means. And so the voltage between them should be 0. There's no wire connecting them. It's just the op-amp behavior that forces this kind of phenomenon. Okay, so that's that measurement. Okay. Okay, then we build the inverting summing amplifier. Okay, so then this is a little bit more tricky. There's a few things going on in this part of the circuit, and so what's happening here? We're going to say, hey, we're going to set up our waveform generator on the oscilloscope to create a cardiac signal. So let's just imagine we have a sensor that detects our, let's see, the pulse, okay? And let's say we get a voltage 100 to 200 millivolts, okay? Then we want to amplify it, and we want to make some sort of offset to shift that voltage up or down to a place where it's easy for us to work with and get useful information. Okay, so what we're going to do is amplify that circuit to make that little small weak signal expand into a larger, more useful signal, and then we're going to add a variable amount of DC offset to shift that signal up or down to get it to a point where we can get some useful information from it. Okay, so the recommendation here is maybe don't use your printed circuit board, because the circuit's going to be a little bit complex and that board will take up a lot of room. You can use it, but you just have to be more careful with how you build your circuit. And in fact, in this part of the lab, you're going to be using 2 op amps. Okay, you're going to be using 2, not just 1. So you're going to have to set up the oscilloscope waveform generator to create the cardiac waveform. So there are instructions given, and you should be familiar with how to use the oscilloscope, or watch the oscilloscope video to familiarize yourself. Okay, so then and then you have to be able to measure the signal too. Okay, use the oscilloscope properly. Okay, so then what you're supposed to do is build the circuit, and then so that's the instructions right here. It tells you how to build the circuit. You're going to be using the work that you did in the pre-lab, and at first basically you're going to build an inverting amplifier, okay, and that's going to magnify the voltage, right? It's going to be almost 11 times larger. Okay, so where is that coming from? I'll show you. Okay, that's coming from this part, and specifically right here. Okay, so AV1 is minus 10.85, so that's why it's saying almost 11 times. Okay, now there's a minus, so it flips the signal. So what's going to happen? So when you do that part, when you build that circuit, you're going to have some sort of cardiac signal that's going to look like this. Okay, so the cardiac signal will look something like this. Okay, I'll take that out, and so let's say it's going to be something small with a little spike, something small. Sorry, I'll make it a little bit better scale. So it's going to be a small spike, and then it's going to go for a bit. You're going to see a small spike. It's going to go for a bit, small spike, and so forth. Okay, so then when you take that signal and multiply it by minus 11, okay, so that's minus 10.85 or whatever it was. Okay, you're going to multiply it by minus 11. That's your input, and then you're going to get amplified signal, so it's going to go along, and that spike's going to be much higher. Oops, sorry, it's minus 11, so actually it's going to go like that, and the spike's going to go down like this, go back up, go across for the same about time, and then shoot down, and so forth. Okay, so the magnitude of those spikes should be about 11 times greater than the magnitude of the spikes on the left. Okay, so then it's going to continue another spike. Okay, so that's going to be your cardiac signal, but your drawing is going to be better because you're going to put in the little nuances of the cardiac signal. I just put the main thing on there. Okay, so that's going to be an inverting amplifier. So you're just going to have one input. Okay, so you're going to be building this part of the circuit, and let's just see if I can. So you're only going to draw the part of the circuit that's visible here. Okay, so you're not going to build this second part of the circuit yet. So that's going to be the minus 11 times amplification. So this input here is going to be waveform generator anyway, that says generator, and that's going to be the cardiac signal. Okay, so then we're going to do something really interesting. We're going to shift the signal. Let's see, where does it say? Okay, right here, adding a DC offset with the potentiometer. Okay, so now what's a potentiometer? So there's a circuit shown right here. Okay, so that's going to be a circuit that you're going to use, and so now it's not. So this is like physically what it looks like. Okay, there's pins on one side and 3 potentiometers. Potentiometers are variable resistors. Okay, so how do they work? So let's just say I'll draw it here. So you're going to have a resistor. Okay, it's going to be like this, and it's going to have a central part with an arrow, and this part with the arrow is adjustable. Okay, and it forms a voltage divider. So you can move this arrow up, or you can move this arrow down. Okay, by twisting the knob on the waveform generator. So that's the knob right there. Okay, and you're going to use the middle one, and I'm going to explain why. So now, how you're going to connect it? There's 3 terminals, and in fact you can see the picture right here. Okay, so it's actually drawn for you. So this is a super nice board for teaching. Okay, so it's exactly what I've drawn there. Now, so what you're going to do is you're going to connect one side to, I'll use green, to plus 15 volts and to minus 15 volts. Okay, so then when you change the wiper up and down, when you turn that knob, it's going to change the voltage divider, and a different voltage is going to appear on the wiper, and that's going to be the part that gets connected to your circuit. So I'm just going to go back up there and show you what that means actually in the circuit. Okay, so let's see, I'll just finish drawing these little things out. Okay, so then what's going to happen is you're going to have that variable resistor in there. Okay, and the voltages on it are going to be plus 15 volts on one side and minus 15 volts on the other, and then this wiper thing is going to connect to your circuit. So as you turn the knob up and down, oh, sorry, and there's going to be a resistor there. Sorry. Oh, whoopsie doopsie. Yeah. So there's going to be a resistor there as well. Sorry, I forgot to leave in the R2 resistor. Okay, that's going to still be there. But as you turn the knob on this guy here, you're going to change the voltage divider, and it's going to put a different voltage into the circuit at that point, and then that's going to shift the waveform up and down, okay? So when you turn the knob, it's going to move the waveform up and down. Okay, so then, what's that going to look like in the circuit that I drew? Okay, so you see this waveform here? That's going to go up or down, okay? And what you're going to want to do, what it's described in the lab, is that you're going to adjust that waveform so that it's mostly above ground. So if we had a ground reference, which we do on the oscilloscope, in fact, so down here it says, right here, it says what that looks like. So there's a symbol here. So it's hard to tell because there's two symbols on here, but this is a ground reference here. Okay, and it goes up to this triangle here, okay? So that means that's where 0 is for that channel of the oscilloscope, okay? So then what we're going to do here, so this thing here, if we put that, that's this thing right here. So that's going to be ground. So we just want the little tips to be going below 0, okay? And there's a reason for that, because we're going to add another op-amp circuit to that inverting summing amplifier, okay? And we're going to add this circuit here, and that's a comparator driving an LED, okay? So this comparator is going to compare the voltage coming in from the inverting summing amplifier, and it's going to compare it to ground. It's going to compare it to 0 volts. So then what's going to happen is if V out goes below 0 volts, like you have to think about how the comparator is working, but if V out is less than 0 volts in this case, then this is going to go to the maximum high voltage, which is going to be plus 15 volts, and this is going to be minus 15 volts, okay? So it's going to shoot high, so this is going to be 15 volts, and it's going to drive current this way through the LED into ground, okay? And when the current is going to go through the LED, it's going to light up, okay? So the LED is a diode, and the bar represents the cathode, okay? And here's a very convenient drawing on the right about how to identify which is the cathode and which is the anode. And you had a little bit of exposure to the LED when you built your op-amp, when you soldered your op-amp PCB. The cathode is the shorter leg, okay? The cathode is the shorter leg of the LED, okay? So that's the top one here, okay? That's the shorter one. There's also a flat part on the base of the LED over here, but sometimes it's hard to spot that, but the flat part around the circular base represents the bar, or that line, okay? So then, let's just talk really briefly about what's happening with the LED. And I have like a page here. Oh, you know what? I'll show you the complete circuit. Okay, sorry. So this is the complete circuit here. I've actually drawn that for you. And so this part here is a summing amplifier, inverting summing amplifier that you're going to build. And remember, this part here is going to be replaced by your potentiometer circuit, okay? So it's going to be replaced by this thing here, okay? So then, the second part of the circuit that you're going to build is the comparator circuit driving the LED. Okay, so that's a complete drawing there for you, okay? So that'll be handy. Okay, so how does that LED work, in fact? Okay, so now what's interesting about LEDs is their properties. So let's imagine we have 15 volts going in, right? So let's say our op-amp is high. It's hit the positive 15, right? Then we have that 1K resistor, and then we have the LED, and then we have ground, okay? So now current's going to flow this way, okay? So you're going to have I. Now what's interesting is when current is flowing through an LED, it actually behaves as a voltage source. Oh, so you couldn't see the top part here. 15 volts. There we go. So then when we have an LED, and when current is flowing through it, it behaves as a very strange device. It actually approximates a voltage source that's reverse biased. So it looks like about 1.4 volts, okay? And then that's still 1K. So then let's calculate how much current is going to flow through there, right? So so that's I. So then I is going to equal 15 volts minus 1.4 volts divided by 1 kilo, and that is going to equal 13.6 milliamps. Okay? So now let's think about it for a second. What's this resistor doing in this circuit? Okay? Now what it's doing, it's acting as a current limit. Okay? It's a current limit, so it's restricting the current that flows so we don't burn that LED. Because imagine if we didn't have that resistor in there. Let's redraw the circuit in a way that it makes sense, and let's draw it like this. So imagine we had plus 15 volt supply. So 15 volts, okay? Okay, and then let's say imagine there's no resistor and we see that 1.4 volt source there, okay? And there's my ground reference. Okay. So now ordinarily that resistor would be right here, right? That would be limiting the resistance. But if there's no resistance, then we're going to have a huge amount of current flowing through here, okay? And what that'll do is it'll damage the LED and burn it out, okay? So that's why in LED circuits we always have a resistor to limit the current. Now there's one last thing that I wanted to mention, and that is why can we only use the middle potentiometer? Okay, these potentiometers have let's see, I'll just make it easier to see. Okay, so these potentiometers, okay, so then the potentiometer has a maximum power of 0.5 watts, which is equal to 500 milliwatts. Okay, so that's the maximum power dissipation that it has. So then, now it's not visible here, but these potentiometers have different resistances. So this one here, oops, wrong color. This one here is 100 kilo. This one here, the one that you're supposed to use, is 10 kilo, and this one here is 1 kilo. Okay? So let's imagine if you're using the 1 kilo one. Okay? So how are you going to connect that circuit? It's going to be like this. You're going to have 15 volts here minus 15 volts there. So that's going to be a maximum 30 volts. And then this is going to be 1 kilo. So what's going to be the power dissipation? So power is going to be V squared over R, which is going to equal 30 volts squared over 1 kilo. And that works out to, what does it work out to? It works out to 0.9, I believe. 0.9, 0, oops, equal to 0.9 watts equals 900 milliwatts. Okay, so then we're going to burn or blow up our potentiometer. Okay, it's going to have too much heat going through it, and that's not going to be good. Okay, so that's for the 1K. So what about, so that's for the 1K. What about for the 10K? Well, that's going to be 30 volts squared, so that's going to be the same divided by 10 kilo ohm, and that's going to be 90 milliwatts. So that's well under the 500 that's maximum. So that one works, okay? This one, it exceeds 500. And then, of course, the 100 kilo ohm is going to be just 10 times less than that, right? And that would work too, except might have some other issues with that circuit. I think a really good value is going to be the middle one. Okay, so use the 10K, the middle one. Don't use the 1K. Okay, that's pretty well it. Hope that's helpful. Good luck with the lab.